It is so-called least squares problem. Okay, well, minimizing so-called convex, we'll come back to this in a minute, convex quadratic function over no constraints. And this is a very nice nonlinear optimization. In general, we say a least square problem is the minimization of the following vectors L2 norm. First of all, what is L2 norm? So given a vector x, want to measure its size, one standard way is L2 norm is the square root of the individual entries squared, summing over all the entries. We often don't like the square root thing. We take the square of the L2 norm. So square of the L2 norm is simply the sum of the xi squared over I. It's a very standard way to measure the length of a vector. And we would like to, in least square, minimize the L2 norm square the length of the vector a, b minus c, where b is our variable, a is a known matrix, c is a known vector. Say if a is n by m, then b is m by 1, a column vector, and c is n by 1, another column vector. In the particular case we just saw, we can also write this problem, minimizing this expression, in this standard form. It looks a little weird, but you soon see it's all right. The matrix is 1, 1, 0, 1, 0, 1. The variable vector we have is b1, ba, bb, and the constant vector term we have is r1a minus r bar on r1b minus r bar. This is our a, this is our b vector, this is our c vector, just to conform to the standard expression that we want to minimize in the least squares problem. You can easily check minimizing this is this L2 norm squared is the same as minimizing this expression. Okay, for example, this is just saying b1 plus ba minus r1a plus r bar, and that's exactly this term, right? And then you can write out the other term, and then just by definition of the square of the L2 norm, you see we're recovering exactly the same objective function.